In today's lesson, we're going to talk about two different things, density and converting measurements. What these discussions will have in common is that in both cases we'll have units of measure that we have to pay attention to as we do calculations. So these things are kind of related to each other. We're going to talk about things we can observe or measure, the macroscopic world, and how we turn that into the symbols that chemists use to communicate things. Let's start with density. Here's a definition. Density is the mass per unit volume of a substance. Substance underlined. Density depends on what substance we have. We can measure the density of an object, but the density of an object depends on what it is made of. It doesn't depend on how much we have. Density is a physical property. Since it's related to mass and volume are both things we can measure without changing the composition of the material we're measuring. Density is a physical property. Oftentimes, density gets measured in grams per milliliter. There's a way to write that, grams/milliliters, or grams over milliliters. It doesn't have to be that way. Density can be measured in any unit of volume divided by, any unit of mass divided by any unit of volume. But for us, that's going to often mean grams per milliliter. So let's take our definition of density and turn it into a formula. Here it is. Density equals mass divided by volume, m over v, mass and volume. So for example, suppose we have an object that has a mass of 96.5 grams and a volume of 5 milliliters. What is its density? Here's our m, here's our v from the problem. Density equals mass divided by volume. Do that calculation, we end up with 19.3 grams over milliliters, and we can write it this way, 19.3 grams per milliliter. You measured mass, measured volume, you can figure out or calculate density. Now here are a couple of things, and both these things are made out of steel. Now turns out there are lots of different kinds of steel, but for the purposes of our example here, we're going to assume that they're made out of the same kind of steel. So paper clips are steel, and these sorts of I-beams that you might use in a bridge or a building are also made of steel. Now, we know that this picture is kind of misleading. Paper clips aren't usually that big. So let's manipulate our picture a little bit. Here's our paper clip over here. Here's our I-beam. Paper clips are little, I-beams are big. These things have the same density. Why? Because they're made out of the same substance. They're both made out of steel. They have the same density, assuming it's the same kind of steel. What if we know the mass of an object, or can measure it, and we know what it's made of, so we can look up its density? Can we figure out its volume? Well, there's a formula for doing that. Volume equals mass divided by density. So for example, if we have something with a mass of 193 grams and a density of 19.3 grams per milliliter, what is its volume? Volume equals mass divided by density. Turns out that the volume is 10 milliliters. Okay. So where did this formula come from? Well, it came from the definition of density. So here's the definition of density. Using the rules of algebra, we can manipulate that formula and we can figure out what V equals if we know D and M. All very legal, based algebraically speaking. What if we can measure the volume of an object? We know what it's made of. We can look up its density. Can we then figure out its mass? Yes, we can. Here's a formula. For example, If we have an object with a volume of 7 milliliters and a density of 19.3 grams per milliliter, can we figure out its density? We can. Can we figure out its mass, that is? We can by multiplying volume times density. Right? M equals V over D. Where that formula come from? It came from the same place as our definition of density. Right? We took our definition of density, we do things to it that are legal in algebra class, and we end up with a formula that we can use, this one down here. If we know volume and density, we can use this formula to figure out the mass of an object or a sample of a substance. Let's shift gears. Let's talk about converting measurements. Now, when we talk about converting measurements, what we're really talking about is converting from one type of metric measurement, from one metric measurement to another. And there are a couple of situations that we'll be in that we need to do this, or we want to do this. Sometimes it's just more convenient to express something in one unit as opposed to another unit. And sometimes we have to express something in a particular unit of measure in order to do a certain kind of calculation. So we want to be able to get from one kind of metric unit to another. And to do that, we're going to use conversion factors. So conversion factors are fractions. They have a measurement in the numerator and a measurement in the denominator, and those measurements are equal. So multiplying by a conversion factor is the same as multiplying by 1, because we're multiplying by something that has a numerator that is equal to its denominator. All right. This is one of the prefixes that we're familiar with in the metric system. The prefix kilo means 1,000. A kilogram, we actually say kilogram. A kilogram equals 1,000 grams. Here's it written down in symbolic form. In the same way, a kilometer or a kilometer equals 1,000 meters. So a kilogram equals 1,000 grams. A kilometer equals 1,000 meters. All right, so knowing that those expressions are true, we can make conversion factors from them. 1,000 grams equals 1 kilogram. Here's a conversion factor. 1 kilogram equals 1,000 grams. Here's a conversion factor. Same way down here with these units that are based on meters. All 4 of these fractions are conversion factors because their numerators equal the denominators in each case. All right, let's use a conversion factor. Suppose we have something that weighs 2,500 grams. How many kilograms does that weigh? So we take our measurement, 2,500 grams, and we use a conversion factor to turn it into some number of kilograms. How did we know which conversion factor to choose? We chose it. We chose the conversion factor that will do what we want it to do. We want it to cancel out grams. We want to get rid of the unit grams and turn it into kilograms. So we chose a conversion factor that has the number of grams in the denominator. Grams cancels out grams, and the number of kilograms in the numerator. We want kilograms to be left at the end of our calculation. We're multiplying this measurement times the numerator, dividing by the denominator. We want grams up above in this overall expression, grams down below, so they'll cancel, and kilograms are left. We chose the conversion factor that does what we want it to do. There's another one of our SI, or metric unit prefixes. Centi means 1/100th, or 0.01. 1 centimeter equals 0.01 meters. There's that written in symbols. We can maybe make it a little easier to understand if we take this equation and multiply it by 100. So we end up with this. 100 centimeters equals 1 meter. All right, if we know 100 centimeters equals 1 meter, we can write some conversion factors. And these are conversion factors because the numerator equals the denominator in each case. Let's use that conversion factor. We have something that's 150 centimeters long. How many meters long is it? Well, we take our 150 centimeters, we multiply it by a conversion factor. Which one do we choose? We choose the one that has centimeters in the denominator and meters in the numerator. So centimeters cancel out and we end up with meters. 150 times 1 divided by 100 is 1.5. Centimeters times meters divided by centimeters is meters. 150 centimeters is 1.5 meters. We used a conversion factor to figure that out. The SI prefix milli means 1,000th or 0.001. So 1 milligram equals 0.001 grams. There's that equation written in symbols. To simplify it, some people's mind, we could multiply it by 1,000, so we end up with 1,000 milligrams equals 1 gram. In a similar way, 1,000 millimeters equals 1 meter. 1,000 milliliters equals 1 liter. Once we have each of those expressions, we can write conversion factors from them. And each of these conversion factors, the numerator, the measurement in the numerator, equals the measurement in the denominator. There is 1 gram for every 1,000 grams. There are 1,000 milliliters for every 1 liter of volume. Suppose we have a substance or a mixture that has a volume of 5 liters. How many milliliters is that? We take our 5 liters, we multiply it by a conversion factor. The conversion factor has a numerator equal to the denominator. We choose a conversion factor that has liters, our given unit, in the denominator, and milliliters, the unit that we want to end up with in the numerator. Liters cancels out. 5 times 1,000 divided by 1 is 5,000. 5 liters equals 5,000 milliliters. We chose the conversion factor that did what we wanted it to do based on the units of measure. There's one more expression that we need to know, one more relationship that we need to know. We're often going to measure volume in milliliters because in chemistry class we use small quantities of things. This little square here is a milliliter. And a milliliter is oftentimes called other things. So 1 milliliter is the same as 1 cubic centimeter. This little cube that I showed you has, and each edge measures 1 centimeter. A milliliter equals 1 cubic centimeter, and a cubic centimeter is sometimes referred to as a cc, particularly in the medical industry. So this is something that we're going to need to remember sometimes. All right, so there you have it. There's a little introduction to the property of density and some of the basics of how we can convert from among different metric or SI units of measure. We'll practice those things in class and we'll use them from time to time during the year.